Hey everyone, welcome back to another lesson in MCV4U. Today we'll be looking at the dot product of algebraic vectors. So if you recall, again, algebraic vectors are expressed in what we call component form. So for example, here if we have, again, this vector u, again, it's equal to u1, u2, and u3. And again, these represent, again, our x, y, and z values when we look at it in a coordinate plane. Here, for geometric vectors, again, we define the dot product to be, again, vector u times vector v is equal to the magnitude of vector u times the magnitude of vector v cos theta. Again, from this particular formula that we're provided, again, from geometric vectors, we can derive, again, the dot product for the algebraic vectors. So here, if we're shown this again on this diagram on the right, we see that we have a couple of things here. Again, we have our vector b. So here we have our vector b. We also have, again, vector a, and then we have our vector c. And so here, again, if we draw a negative vector b, so here if we draw a negative vector b, and then we take it from the origin to vector b, negative vector b, we see here that we can represent vector c as vector a minus vector b. So when we look at that, again, if we use the formula that we have, we can see that vector c squared is equal to vector a squared plus vector b squared minus 2 vector a vector b cos theta. And so here we see again that we have this formula again created based on cosine law. Again, if we're looking at our theta, we have a theta value here and our other angle there as well. And so here we know that AB cos theta we can represent as the dot product of A times B. So here we can rewrite it as vector C squared is equal to A squared plus B squared minus 2. And again, here this vector A times vector B cos C, we can represent that as here the dot product of vector A times vector B. And we see that based on our geometric vector equation that we saw up there. And so here, again, if we write it in component form, then vector A is equal to a value x, and the a value for y, vector b. See that here we have the b value of x and the b value for y. And then finally for vector c, you see that we represented that as vector a minus vector b. And so that equals to ax minus the bx, and then ay minus by. So the a value of x minus the b value of x, and the a value of y minus the b value of y. Here, then we're trying to find the magnitude of vector a, and that'll be equal to the square root of the a value of x squared plus the a value of y squared. Vector b, again, will be the b value of x squared plus the b value of y squared. And then for vector c, it'll be the square root of ax minus bx squared plus ay minus by squared. And so here, again, if we rewrite our equation and sub in what we just solved for in terms of the magnitude, here we'll get ax minus by squared plus ay minus by squared. And so this entire thing represents magnitude of c squared. That's equal to a x squared plus a squared. This represents the magnitude of a squared plus bx squared plus by squared. That represents the magnitude of b squared, and then minus 2, the dot product of vector a times the dot times b times vector b. And so here, if we expand what we have here, we'll have ax squared minus 2 ax bx plus bx squared plus a y squared minus 2 ay by squared is equal to a x squared plus a y squared plus bx squared plus by squared minus 2 dot product of vector a times vector b. So here we can cancel a couple things out. Ax squared, bx squared, and the by squared. There should be an addition here as well. Plus by. Let me just move this over here. And so the by squared will also cancel out. And so here, what we'll be left with is we'll be left with negative 2 ax bx minus 2 ay by Again, this ax squared will also cancel out as well. And equals -2 vector A and vector B. What we'll do here, we'll divide everything by 2, by -2. And here we'll get ax bx plus ay by is equal to the dot product of a vector A times vector B. So in summary, again, what's important? So that in 2 space, or R squared, again, the dot product of vector A times vector B is equal to ax bx plus ay by. So similarly, if we look at it in 3 space, or R cubed, it's equal to ax bx plus ay by plus az bz. And so here, to isolate for the angle, so again, here we see that dot product of vector A and vector B is equal to ax bx plus ay by is equal to the magnitude of vector A times the magnitude of vector B cos theta. And if we divide, again, everything by the magnitude of vector A and the magnitude of vector B, we see here that cos theta is equal to the dot product of vector A and vector B over the magnitude of vector A and vector B. This is for the algebraic vectors. Okay, so let's look at the examples here. So it says find the dot product of vector u is equal to 2, 5, 9, and vector v is equal to 1, 0, and 4. Okay, so here, if we write it in component form, so vector u is equal to 2, 5, and 9, and vector v is equal to 1, 0, and 4. And so here we see that our x values are 2 and 1, y values are 5 and 0, and our z values are 9 and 4. And so therefore, if we're calculating for our dot product, so vector u times vector v, it'll be 2 times 1 plus 5 times 0 plus 9 times 4. So that gives us a value of 38. And here, again, it says calculate the angle theta to the nearest degree between the vectors. Vector m is equal to 3, 6, and vector n is equal to 4, 1. Okay, so first thing we'll do here is we'll draw a grid just to plot our points. And so here we see that this is our vector n for 1, starting again from the origin. And then our other for vector m at 3 and 6. And so here, again, if we write it in our component form, vector m will be 3, 6, and vector n will be 4 and 1. So again, if we recall our formula, cos theta is equal to the dot product of vector m times vector n over the magnitude of vector m and the magnitude of vector n. So here we have cos theta is equal to 12, so 3 times 4, 3 times 4, and then plus the, and then plus 6 here. That's all over, again, the magnitude of vector m and the magnitude of vector n. So we'll calculate this here on the side. Again, the magnitude of vector m is equal to the square root of x squared plus y squared. So that's here, it's equal to square root of 3 squared plus 6 squared, which is equal to square root 45, which is equal to 3 square root 5. And so here, again, the magnitude of vector m will be square root 17. So here, if we write that back in our equation, we have magnitude of vector m, which is 3 square root 5, and the magnitude of vector n, which is square root 17. And so here, we get theta is equal to cos negative 1 of 18 over 3 square root 85. And therefore, we get theta is equal to 49 degrees. Example 2 says, for what values of c are the vectors vector u is equal to 1, c, and 2, and vector v is equal to 4, 5, and c perpendicular? So here we know that if it's perpendicular, the dot product of vector u and vector v, when you multiply those together, will be equal to 0. So here we get 4 plus 5c plus 2c is equal to 0. 7c is equal to negative 4, and therefore c has to be equal to negative 4 over 7. Again, for the values of c for these two vectors to be perpendicular. Last example here says if vector u is equal to 1, 2, 3, and vector v is equal to 2, 1, 4, find the vector perpendicular to both u and v. Okay, so what we'll do here is we'll let vector a be equal to x, y, and z, and that's going to be perpendicular to both vector u and vector v. So here we see that vector a has to be perpendicular to vector u, which means that the dot product of vector a and vector u has to be equal to 0. So that means here x plus 2y plus 3z is equal to 0. Same thing. Again, vector a has to be perpendicular to vector v, which means that the dot product of a times v is equal to 0. This means that 2x plus y plus 4z is equal to 0. What we'll do here is we'll multiply the first equation by 2. So here we have a system of equations. We have 2x plus 4y plus 6z is equal to 0. And we have 2x plus y plus 4z is equal to 0. Here we'll use elimination. We can subtract the two equations. 2x minus 2x, that gives us 0. 4y minus y gives us 3y. And 6z minus 4z is 2z is equal to 0. And here we have 3y is equal to negative 2z, and y is equal to negative 2 over 3z. Now we're going to sub this back into our equation of x plus 2y plus 3z is equal to 0. And so here we have x plus 2 times negative 2 over 3z, which we replaced with y from y, plus 3z is equal to 0. Here, if we expand this, we get x minus 4 over 3z plus 9 over 3z is equal to 0. So we wrote that as 9 over 3, so we can have, again, our common denominator of 3. So here we have x plus 5 over 3z is equal to 0. And so here we have x is equal to negative 5 over 3z. From there, then we see here that vector A will be equal to negative 5 over 3z, negative 2 over 3z, and z. That's equal to z. Again, if we factor that out, we have z negative 5 over 3, negative 2 over 3, and 1. Okay, so here we can see that, again, we can sub in a value such as negative 3. So here, if we let, say, z is equal to negative 3, we would get that vector A is equal to 5, 2, and negative 3. But here we can see that there's an infinite number of values that we can pick for z, again, to get one of these vectors that's perpendicular to both u and v. So here, if I picked z is equal to 9, for example, then I'd get vector A is equal to negative 15, negative 6, and 9. So there's an infinite number of possibilities that we can use here to, again, solve for this question.